So last time we talked about how matrices can be used to solve systems of equations. And today we're going to look at a couple of other ways a couple of other types of equations that can also be used, that can also use matrices to solve them. And so the first thing we need to talk about here is what are called vectors. Now, and certainly vectors are going to come up a lot throughout this entire course. So it's definitely worth the time that we take now to understand what they are. I have to assume, I guess I won't assume, but there's a decent chance that some of you have worked with vectors previously, maybe in a physics class, or maybe even for those of you who've taken Calculus 3, a lot of times vectors are part of that. So for some of you, this may not be new, but that's okay. So what do I mean by a vector? So a matrix with only one column is called a column vector or just simply vector. For a little bit later in the course, we'll talk about row vectors, but mostly just column vectors. And so here's a couple of examples. In this case, each of these vectors have two components. We could also talk about more than just two, and we certainly will, even before we're done today. I want to point out that these two letters here, U and V, are both bold-faced. In the text, that's what they do. When I write a vector, I can't, if I write the letter U, I can't really write it bold-faced. So when I write a vector, I'm going to write it with a little arrow over it to represent that it's a vector. But anytime you see a letter that's bold, that means that it's a vector. The set of all vectors with two entries is this R2, or I mean R squared is fine too, but generally I'll read this as R2. And so this represents any vector with two entries. And the reason is because each of those two entries could be all real numbers. The first entry could be all reals, second entry could be all reals. So we just call it R2 because I don't know, that's why. Because there's two different real numbers to pick, I guess. Two vectors are equal if the corresponding entries are equal. So basically that's what I mean by two vectors being equal, is that the components are exactly the same. Okay, graphing wise, order pairs in the xy plane, like vectors in R2, are represented by two numbers. What I mean is, if we were to graph a point like the point 3 comma negative 1, we could also represent this with the vector 3 negative 1. So notice that we have these two, at the bottom here, we have the point 3 comma negative 1. Sometimes it's useful to include a directed line segment with an arrow from the origin to the point. So instead of graphing the point 3 comma 1, we could instead draw this vector starting at the origin and ending at the point 3 comma 1. And so this would be that vector 3 negative 1, like that. We're not interested in all the points that are on the segment. We're just interested in the point where it ends. So a vector has both magnitude and direction. You probably heard that in previous courses. So this would be the vector we're talking about. But again, we're really just interested in where does it stop if we start at the origin. We want to talk about adding and subtracting vectors. If I give you the components, adding and subtracting two vectors just means add or subtract the corresponding pieces. If we want to multiply by a scalar, meaning multiply by just a number instead of another vector, what's going to happen is we're going to multiply each entry of the vector by that scalar. So just as a couple of examples here, we've got U and V. If I want to talk about 3U, again, that just means take the entries in vector U and multiply them all by 3. So this would be 6, negative 9. That's it. And 3U minus V. So that means I would take this vector 3U and subtract from it vector V. And again, adding and subtracting vectors means we subtract the corresponding pieces. So 6 minus 4 gives me 2. Negative 9 minus 1 gives me negative 10. So this new vector represents that combination of these two vectors U and V. Okay, now graphically, what does this represent? Again, U represents the vector from the point 0, 0 to the point 2, negative 3. So maybe something like this would be vector U. And then vector v goes from the origin to the point 4, 1. So maybe here's vector v. But the question now becomes, what does it mean if we find 3u? How does that compare with the original vector u? What does it mean to subtract the two vectors? So if two vectors are in R2, again, R2 just means they lie in the xy plane. If two vectors are in R2, then u plus v corresponds to the fourth vertex of the parallelogram formed by u and v. So here's what I mean by that. So consider these two vectors u and v. So if I draw the parallelogram, meaning if this is vector u, then this is also vector u, just moved over. Moved over so that it starts where v ends. So here's vector v, and here's another copy of vector v. Again, for anybody who's worked with vectors before, you know that a vector has direction and magnitude. Position does not matter. And so we can move them around and they're still the same vectors. And yeah, so if you create this parallelogram, this starting at the origin and ending all the way out here is what we mean u plus v. Another way to think about it, it just depends on how you want to think about it. It doesn't really matter. But another way to think about it, if we were to follow vector u, so here's vector u, and then as soon as we stop u, now we follow vector v. So the end of u becomes the beginning of v. Wherever we end up, the direct line from the origin to that ending point is that vector we're talking about, u plus v. So this is just another way to think about the same idea. So this is what it means to add two vectors. If we want to talk about multiplying by a scalar, if c is a scalar and v is a vector, then c times v is the vector in the same direction as v that has the length c times as long as v. So multiplying by a scalar does nothing more than change the length. Multiply, it makes it double or a third or whatever. The only other change that could happen is if c is negative, now we're going to go in the opposite direction. So if we want to think of this as vector v, 1/3 v would be, notice, same direction, same slope, if you will, but now the length is 1/3 as long. And then this example here, negative 2v, notice that the length, if this length right here is vector v, this would be basically two of those. But notice that because it's a negative, notice that the arrow is at the other end. Same slope, but now we're going the opposite direction. Okay, these ideas can be extended to n-dimensional space, Rn. Obviously, as 3 dimensions, we can probably wrap our brains around pretty well. It's just a little hard to draw it in, a two-dimensional surface, but we can talk about the R3. But these ideas can also be extended to higher dimensions. It's just a lot harder to visualize, even 4D. And we can talk about that a little bit, but certainly as a video, I think it's a terrible idea. But it's, already it's hard. But we will certainly be talking broadly about higher dimensional vectors. We just may not talk about them geometrically, as we have been with the last couple slides. The zero vector, I'm sorry. So this would be an example of an nth dimensional vector. And then the zero vector just means the vector where all the entries are zeros. Yeah, that's it. Also, please notice that the zero here is a boldface. So if I were to write the zero vector, I would write a zero with a little arrow over it. Here are some properties, some basic properties of vectors. This is the commutative property, where we can switch the order of addition and not have any problems. This would be the commutative property, where we can switch rather than doing, we can switch the order that we do the addition of 3 different vectors. This is the zero property, meaning that if you add 0 to a vector, it changes nothing. This is called the inverse property. The idea being here that if you've got a vector, adding its opposite results in the zero vector. This would be the distributive property, multiplying one scalar by 2 vectors. Here's the distributive property, 2 scalars by 1 vector. This would be, looks like the commutative property for multiplying by scalars. And then this is the um, basically multiplying by 1. I think it's the identity property for scalar multiplication. It doesn't matter. I'm not going to test you on any of those names. You don't need to memorize the names. You don't need to memorize the properties. It's just useful to remember that they exist and remember how to. That yeah, they could save you a little bit of effort when you do some problems. But at no point am I ever going to ask you to recite these properties or anything like that. Okay. Here's the next thing we need to talk about. And I said this earlier when it came to vectors. This concept that we're about to introduce is a really important one that's definitely going to come back a lot in this course. And it's the idea of a linear combination. So a linear combination of vectors involves multiplying each vector by a constant coefficient and then adding the results. Basically, a linear combination means creating a new vector where we take a bunch of vectors, all these v's, each one is multiplied by a scalar coefficient, and then adding all the results together. And so this new vector y is called the linear combination of all these v's, v1, v2, up through vn. So that's what I mean by a linear combination. So as an example, this vector 14, -7 is a linear combination of these two vectors, because if I were to do 3 times v1 plus 2 times v2, let me do these really quick. So this would be 6, -9, and this would be 8, 2. And notice if I add those together, I'm going to get 14, -7. So U is a linear combination of V1 and V2 because we can find these coefficients that result in that could be used to combine V1 and V2, and the result is that U. And those coefficients are called the weights of the linear combination. So again, in order for U to be a linear combination, we need to be able to find those coefficients that would result in a combination of V1 and V2 giving us U. So let's determine if B can be written as a linear combination of A1 and A2. Now, there are ways to kind of plug and chug and see if you can come up with any coefficients. Again, the whole point is what do we multiply this vector by and multiply this vector by, so that when we add them together, this is our result. There are ways to mess around with that and see what happens. How deep do I want to get into this right now? So let's think about this for a second. What I'm really asking is I need to find a coefficient to go in front of the 1, -2, 5, -5, and another coefficient to go in front of that 2, 5, 6, so that the result is 7, 4, -3. That's really what I'm looking for. And by the way, you may be able to eyeball it now. You may be able to just kind of make some guesses. But what if the answer was no? What if it was no, B cannot be written as a linear combination? Well, it's not just enough to say, you know what, I tried everything, I give up. You need some rigorous way to really show that there is no solution. So let's play around with this a little bit. Let's bring those C's inside. So this would be C1 plus 2C2, -2C1 plus 5C2, and -5C1 plus 6C2. And we want that to be equal to 7, 4, -3. All right. Now remember, if these two vectors are equal to each other, that means that the corresponding pieces have to be the same. C1 plus 2C2 equals 7. -2C1 plus 5C2 has to be equal to 4. And -5C1 plus 6C2 is equal to -3. So really, when I ask the question, is it a linear combination? Really, the question I'm asking is, what are the coefficients? And to find those coefficients, what I really need to do is solve the system of equations. So let's solve the system of equations. Let's set up an augmented matrix. So this would be 1, 2, 7. Let's put a little bar here. -2, 5, 4, -5, 6, -3. By the way, after this example, I don't expect you to show all the work I've shown so far. I have no doubt that after this example, you will be able to say, oh, okay, A1, A2, B, let's take those, let's take all of them, and let's put them into this augmented matrix. Notice that the first column of the matrix is A1, the second column of this matrix is A2, and the right side is B. So we can use an augmented matrix to solve this, to answer this question, basically to determine if A1 and A2 are a linear combination, or can be, we can find a linear combination to get B. All right, let's now work with this matrix. Let's reduce this. Now, please notice the problem just says, can it be, is B a linear combination? So really all I need to ask here is there a solution? I don't actually need to find the solution. I just want to know, is there a solution? So let's leave the top row the way it is. The second row, I'm going to do row 2 is going to be replaced with row 2 plus 2 row 1. So 0, 9, 18. And then row 3, I'll replace with row 3 minus 5 row 1. So the top row times plus 5 row 1. So top row times 5 plus the bottom row is 0. Top row times 5 plus the bottom row is 16. Top row times 5 is 35 minus the bottom row is 32. Okay, 1, 2, 7. If I'm going to replace row 2 with basically 1/9 row 2. Divide everything by 9 here, so we get 0, 1, 2. And then notice if I divide the bottom row by 16, I'm going to get the same thing. So 1/16 row 3. So it'll also be 0, 1, 2. And so finally, if I just replace row 3 with row 3 minus row 2, we're going to get 1, 2, 7, 0, 1, 2, 0, 0, 0. Okay, finally, let's remember, as long as let me think for a second here. As long as the right column is not a pivot column, then there is a solution, right? Notice that my pivot columns are the first and the second column. There is no pivot in the last column, so therefore there is a solution. Probably a better way of expressing that would be to say that the system is consistent. So therefore B is a linear combination of A1 and A2. There we go. So by showing that that there's a solution, we are saying that it is a linear combination. Cool. To summarize something I said just a moment ago, notice that the columns of our augmented matrix were A1, A2, and B. If we wanted to, we can abbreviate it this way. Let me put the little augmentation bar there. So that would be a nice way to abbreviate the work if you wanted to, if you ever found the need to. So because A1 is a vector, it's basically saying the entire first column is that vector. And then same for A2 and same for B. Okay. In general, a vector equation, x1, a1 plus x2, a2 plus x, so on up through x and an equals b. So this vector equation, by the way, in the last example I used c's. In this equation I'm using x's. Who cares what letters we use? The x's here are the same as, are the weights, just like those c's were the weights earlier. A vector equation has the same solution set as the linear system whose augmented matrix is this one. Again, I'm going to little bar here. So this now is a connection between this vector equation, again, the idea of linear combination, and the linear system that we worked with last class. So for example, if I wanted to just take this system of equations and convert it to a vector equation, we saw last class how to convert it to an augmented matrix. This would be the same as the vector equation, where x1 is multiplied by all those coefficients on the x1, so 3, -1, 2, plus x2 times all of the coefficients for x2, so -2, 5, -1, plus x3 times all of those coefficients, so 1, 2, -5, and that's equal to the right side, 4, 6, 2. That's it. So we've now converted this linear system into a vector equation, just a different form of basically asking the same thing. Okay. Let's see here. If these vectors are v1 up through vp are vectors in Rn, then the set of all linear combinations of these vectors is denoted as, okay, so this is the span of v1 up through vp. So first of all, please notice I'm deliberately making this subscript p different than this n. Basically, okay, as soon as you introduce letters, things get a little confusing. So let me use some concrete examples here. Let's say that we're talking about R10, okay, all the vectors with 10 components. I'm considering vectors in R10, but I'm considering less than 10 of them. So let's say I'm considering 3 vectors in R10. So each of those vectors has 10 elements, but I'm only considering 3 of them. Okay, so that's it. So notice, so what's going to happen is when we start talking about the span of these vectors, we're talking about all the different vectors that are a linear combination of these 3. Basically, all the different ways I can do C1, C2, and C3, all the different C's that I could pick and add them all together. Any vector that could result from that is in that span that we're talking about. And this is a subset of Rn. Again, when I do this combination, this vector is also in our R10 in our example. Not all vectors in R10 will be in this span. Not all vectors in R10 will be a linear combination of these 3. But the span represents all the ones that can be a linear combination of these 3. Yeah, okay. So it's basically all the different vectors that we could get when we pick different C's. Okay, let's think about what this means visually. Now again, when we talk about R10, I have no idea how to visualize a 10-dimensional vector, but let's go back to 3 dimensions. If we're in 3 dimensions, the span of one vector, now again, this would be the set of all vectors that would be some constant times that vector. Well, multiplying a vector by a constant just changes the length but doesn't change the direction. So if this right here is vector v, the span would represent all vectors that are along that line. Now it's the line that goes through the origin, but any vector on that line would be the same direction as v but just a different length. The different c's would dictate the different lengths. The span of 2 vectors. So here's vector u, here's vector v. Now this basically represents, any constant times u plus any other constant times v. And so the span would be all the different distances that I could go in the u direction and all the distances in the v direction, and then adding those together to create these new vectors. So this would be a plane, again, through the origin, but this would be the plane that's defined by that parallelogram created by u and v. Okay, so if I were to ask you, determine if this vector is in the plane generated by these 2 vectors a1 and a2. This is the same as asking, is B in the span of these two vectors? Which is exactly the same question I was asking earlier. Is this vector B a linear combination of A1 and A2? So to answer this question, we're going to create the augmented matrix. Again, the first column is A, so 1, -2, 3. Second column is, first column is A1 and then A2, so 5, -13, -3. And then the right column is B, so -3, 8, 1. So again, this question is exactly the same as the last one. So we're going to solve it the same way. We're going to reduce it. We're going to see what happens. So let's see. So R2, I'm going to replace with R2 plus 2R1. By the way, if in this lesson, I'm going to keep denoting what I'm doing at each step. After this lesson, or maybe after the next one, I don't know. We'll see. I'm probably going to stop doing that and just verbally saying it because we will certainly be doing row reduction throughout the entire course. And so I think it's at a certain point we just kind of get used to it. So the top row we're going to leave alone. So double the top row and then add the second row. So 0, -3, 2. And then R3 is going to be R3 minus 3R1. So multiply the top row by -3 and add the bottom row. Multiply the top row by -3 is -15, plus the bottom row is -18. Then top row times -3 would be 9, plus the bottom row is 10. Okay, let's see here. Top row's fine. Second row now is fine. It'd be nice to have a 1 in that spot, but it doesn't really matter. And then my row 3, so I'm going to do 6 times, how about -6 times row 2 plus row 3. So multiply the second row by -6 and add the bottom row. And I'm getting -2. Okay, we now have it in echelon form. Finally, we're going to notice that because there is a pivot position in the last column, this tells me that the system is inconsistent. That's easy for me to say. System is inconsistent. Therefore, B is not in the span of A1 and A2. There we go. Okay, right on. So there is no way to find a linear combination of A1 and A2 and have the result be B. Cool. Okay, so that's vectors. The other thing I want to talk about here is what's called the matrix equation. So let's let A be the matrix made up of these. Now again, remember, A1 is noticed as bold, so that's the vector A1 is the entire first column. And so A is made up of these vectors where the first column is A1, the second column is A2, and so on. So each of these A's is a vector in Rm. Okay, so that means that each of these columns has m elements. So that tells me that there are m rows. And notice that the last one is labeled here n. That means that there are n columns. So this is an m by n matrix. Just worth observing that that is the case. We're going to let x be a vector in Rn. Fine. Then the product of A times x is the linear combination of the columns of A using the entries of x as weights. So again, let's make sure that this makes sense. So A times x, A is an m by n matrix, x is an n by 1 matrix. And so the result is going to be an m by 1 matrix. Okay, I don't know if that'll help us, but it's just worth keeping track of everything here. Okay, here's what this is saying. So if I do A times x, remember, this is a whole matrix. Each of these A's is a vector. And so if I take a matrix times this vector, That is exactly the same as saying that the first entry of that vector is the weight for the first column of A, and the second entry of the vector is the weight for the second column of A, and so on. So this is a way of, we haven't really talked about multiplying matrices, but this is a way of multiplying matrices, basically. This is a way of saying, okay, here's how I take a matrix and I multiply it by a vector. So let's look at a couple of examples here. Let's take this matrix and multiply by this vector. Now again, what we're saying is, to evaluate this, we're going to take the first column of the matrix, 1, 0, and we're going to multiply it. The weight, the coefficient, is going to be the first entry of the vector, 4, plus the second column of the matrix, 2, -5, and its weight will be the second entry of the vector, which is 3. And then finally we have 7 times the third column, which is -1, 3. Let me say also, by the way, some of you, again, may already have experience with matrices, may have experience with vectors, and that's fine. If you have another way to multiply these, if you've learned matrix multiplication before and you know how to do this, feel free to use it. That's okay. But it is definitely worth your while just to remember that this is one way of thinking about a matrix times a vector, is the idea that the entries of the vector are the weights for the linear combination of the columns of the matrix. Anyway, let me simplify this. So this becomes 4, 0 plus 6, -15 plus -7, 21. If I add those all together, 4 plus 6 minus 7 is 3. Then 0 minus 15 plus 21 is 6. So the result here is the matrix, or is the vector, excuse me, 3, 6. Awesome. Okay. Let's try this one here. Okay, so now again, the idea is take the first column of the matrix, so 2, 8, -5, and its weight is going to be the first entry of the vector, which is 4. Take the second column of the matrix, -3, 0, 2, and its weight will be the second entry of the vector, which is 7. So this would be 8, 32, -20, plus -21, 0, 14, and then finally add, oops, there is that. Okay, equals. And then finally, adding two vectors means add the corresponding components. So 8 plus -21 is -13, I think. Sure, why not? 32 plus 0 is 32, and then -20 plus 14 is -6. Okay, so there's my answer here. And let's look at one more here. There we go. Okay, so we have a matrix times a vector. So I'm going to take the first column, which would be 2, 8, -5, and its weight will be the first entry of the vector, which is 4. Take the second column, which is -3, 0, 2. Its weight will be the second entry of the vector, which is 7. And now we have a problem because I'm out of columns, but I still have this weight remaining. So for this reason, this product actually is not possible. Okay. First of all, I'm not going to ask you to do this problem on a test because I'm not going to say find the product. Oh, haha, just kidding. There's no answer. I just want you guys to realize not all products can be done. In this case, it cannot be done. Okay. By the way, it just occurred to me, this conversation here about figuring out how big our matrix is, honestly, now that I'm thinking about it, I don't remember if we actually did that last lesson. So if that doesn't make any sense, you know what? Don't sweat it. Not a big deal. So I'm sorry if that was confusing. Um, anyway, in this example, again, this is a product that just doesn't make any sense. It's not done. Okay, now let's go back to what we've done before. What we started with last class. This is a linear system. Linear systems can be expressed in three different ways, and we pick the one that's most convenient to whatever problem we're doing. So here's a linear system. Um, we've already discussed another way of expressing that linear system is as a vector equation. And now think of this vector equation. Isn't this vector equation, oh, here's a vector times a weight. Here's a vector times a weight, and here's a vector times a weight. So couldn't we then express that as a matrix product? So here's those three vectors, and here's those three weights, x1, x2, and x3. So again, it is possible to go from from a vector equation to a matrix equation. But keep in mind, all three of them will be represented by the same augmented matrix. All three of them, to solve any of them, we would still use the same augmented matrix. So that would be 1, 2, -1, 0, -5, 3, and then the right side would be 4, 1. So all three of these equations we would solve using the same augmented matrix. Please notice, by the way, in this matrix equation, this matrix is nothing more than that coefficient matrix that we discussed last class. So that's just worth noting that. Okay, is this equation, ax equals b, consistent for all possible b1, b2, and b3? So again, this is a matrix equation. Okay, it's a matrix times a vector equals another vector. That's not really important. The important thing is, let's set up the augmented matrix and let's see if we can answer this question. Is this consistent for all possible B1, B2, and B3? Because again, all three of those equations can be solved using the same augmented matrix. So we have 1, 3, 4, -4, 2, -6, -3, -2, -7, B1, B2, B3. Okay, let's play around with this a little bit. First row is fine. Once again, please notice, in fact, all the examples we've seen so far today, um, we're not actually asked to solve. We're just asked, is there a solution? Okay, that's nice because it means as soon as we've identified the pivot positions, we're done. We don't need to do anything else. Row 2, so I'm going to take 4 times row 1 and add it to row 2. So it'll be 0. 4 times row 1 plus row 2 would be 14. 4 times row 1 would be 16, minus 6 is 10. Okay, now 4 times row 1 would be 4b1, and then we're going to add that to b2. Okay, so the right column is going to get a little bit messy here. Row 3, so now I'll do 3 times the top row and then add it to the bottom row. So 3 times the top row plus the bottom row is 0. 3 times the top row plus the bottom row is 7. 3 times the top row would be 12 plus the bottom row is 5. 3 times the top row would be 3b1 plus the bottom row would be b3. Okay. Once again, it'd be nice to get a 1 in the next pivot position, but it's not that important. So row 3, I'm going to do, how about -2 times row 3 and add that to row 2. So we got 1, 3, 4, b1 is 0, 14, 10, 4b1 plus b2. All right, so let's see. I'm going to do -2 times the second row plus, I'm sorry, -2 times the bottom row plus the second row. So that's 0, 0. -2 times the bottom row plus the second row would be 0. -2 times the bottom row plus the second row is, let's see here. So it'd be -2b1 plus b2 minus 2b3. I believe that is correct. Let me double check that. Negative 2 times the bottom row plus the second row. Yeah, I believe that's correct. Okay, so now the question we have to ask, again, the question is this equation consistent for all possible b1, b2, and b3? And the answer is no, it's not. If this number here had been non-zero, then I could say yes. Remember, the big question is, do we have a pivot right here? And the answer is maybe, right? If this number had been non-zero, then there's our last pivot. And the answer is yes, it's consistent no matter what we pick for B1, B2, and B3. But notice that this time there is a possibility that we get a pivot in a spot we don't want it. So is it consistent for all? The answer is no. It's inconsistent if negative 2b1 plus b2 minus 2b3 is non-zero. If what we ended up with in that lower right hand corner had been is anything other than zero, then we have something that is inconsistent. So, the answer is no, it's not. There are lots of b's that would make this inconsistent. So, cool. Okay, next up, we have some properties that are all going to be equivalent. So let A be an n by m or an m by n matrix, and let B be a vector in a R sub m. The following are equivalent. Now, when I say the following are equivalent, we're going to see that statement again later in the course. What I mean is either every one of these things is true or every one of them is false. If one of these things is true, then they're all true. If one of these things is false, then they're all false. Okay, so here are the statements. The first statement is that the equation AX equals B has a solution for all B and Rm. Okay, so the first statement is no matter what B I pick, there will be a solution. So right away, this is not the last example, right? In the last example, there was no solution for certain B's. So if this statement is true, then we would not end up with a pivot in that lower right-hand corner like we did in the last example. Okay, so first statement, there is a solution no matter what. Second statement, every B is a linear combination of the columns of A. These, again, these are equivalent statements. They basically mean the same thing, right? If B is a solution to the matrix equation, then B is basically it's a solution to the vector equation, right? B is a linear combination of those columns of matrix A. And the third one, the columns of A span Rm, okay, meaning every vector in Rm is in the span of those columns. This basically says the same thing as statement number 2, right? If every B in Rm is a linear combination, that means that all of Rm, all the vectors in Rm are in the span of the columns of A. Again, all three of these things are exactly the same thing. They say all the same thing. And then the fourth thing here, A has a pivot position in every row. Okay, so this is one that is not necessarily as obvious. I want to point out, and this is really important here, please notice that this is about the coefficient matrix A of the linear system. It is not the augmented matrix where that B is thrown in there. So when I say A has a pivot position in every row, what that means basically is there can't be a pivot in the last column. Because if that means that let me say that one more time. If A has a pivot position in every row, then the augmented matrix can't have a pivot position in the lower right-hand corner, because we already know that there's going to be a pivot in every one of the rows of A. So notice, let me go back to this last example for a moment. If this right here is my matrix A does not have a pivot in every row, right? This row has no pivot, which now opens up the possibility that there's that pivot in the lower right-hand corner, which led to that inconsistent. That was going to be consistent only if A has a pivot in every row before we even get to the point of augmenting it with a vector B. Okay, so if I ask the question, can AX equals B be solved for any B in R3? That's what I believe that's the first statement. So we can answer that question by basically reducing this and see if the fourth statement is true. Let's reduce this. Let's see if there really is a pivot position in every row. So we've already got matrix A. I'll just rewrite it here. 1, 0, negative 1, 6, 7, 1, negative 1, 14, 5, 1, 1, 2. And please notice this is not the augmented matrix. We don't have B. We don't even need to write out B because really all I need to do is ask the question about matrix A. Right. Let's replace row 2. How about negative 7 row 1 plus row 2? So I get 1, 0, negative 1, 6, 0, 1, 6, negative 42 plus 14 is negative 28. Yeah, cool. And then row 3, so we'll do negative 5 row 1 plus row 3. So top row times negative 5 plus the bottom row, negative 28. Well, that looks familiar. Finally, if I just replace row 3 with row 2 minus row 3, 1, 0, negative 1, 6, 0, 1, 6, negative 28, and then a bunch of zeros. Okay. Well, here's the answer. The answer is no. It cannot be solved for any B because R, where did I get R? Sorry. A does not have a pivot. I can't spell. In every row. There we go. So the answer is no. It can't be solved for every B because it does not have a pivot in every row. In other words, if I were to try to augment this, it's possible that there's something here that's non-zero, which means inconsistent, means it is not a solution. There's no solution. Okay, we could ask, do the columns of A span R3? It's the same question, right? It's the exact same question. All four of those statements were the same. So once again, we can answer this question in the exact same way. We can do row reduction and we can figure it out. 7, 1, 2, 5, negative 1, 6, negative 2, 0, 4. I think to make my life a little bit easier, I'm going to switch the first and third rows. And in fact, I'm going to be a little sneaky and divide that third row by 2 at the same time. So we're going to, how about negative 2? Okay, let me just write it so you can read it. How about that? Erase. Okay, let's try this again. So row 1 and row 3 are going to switch, and I'm going to make it negative 1/2 row 3. I'm just going to reduce that a little bit. So we got 1, 0, negative 2 on top, 7, 1, 2 on the bottom, and the middle row doesn't change any. Okay. Now, row 1 is fine. I'll do row 2 is going to be, how about negative 5 row 1 plus row 2. So that would be 0, negative 1, 16. I think if I did it right. Yep. and then row 3. So we'll do -7 row 1 plus row 3. So 0, 1, 16. Just make sure I didn't make a mistake here somewhere. Feel like I might have. It's okay if I didn't. No, I think we're good. Okay. Cool. And then finally, row 3 gets replaced with row 2 plus row 3. So we go 1, 0, -2, 0, -1, 16, 0, 0, 32. Once more, I don't need reduced echelon. I don't need a solution. All I want to know is there a solution? So do the columns of A span R3? The answer is yes, because all rows of A have pivots. There we go. Awesome. Okay. Um, you know what? We're not even going to do this. I mentioned earlier multiplying matrix times a vector. There are other ways to do it, and we will certainly look at those later in the course, but I'm just going to skip that right now. Last thing we need to talk about is the identity matrix. So the identity matrix is a square matrix. Remember, actually, I don't know if I've said this before, but square just means that it has the same number of rows as it does columns. So it's a square matrix that has a 1 on its main diagonal. So those ones going, remember, main diagonal means row 1, column row 1, row 2, column 2, row 3, column 3, and so on. So ones in the main diagonal, zeros everywhere else. And I'm calling this R4, or sorry, I'm calling this I4 because it's a 4 by 4 matrix. You know, you can have an identity of any size. And then finally here, multiplying any vector by I results in the same vector. So I times X is just X again. So that's it. It's basically like multiplying by the number 1. That's what the identity is. Okay, that is the end of the lesson. Thank you very much for watching.